Awesome. So my name is Milena Talavera, and I'm an engineering manager on the infrastructure team at Slack. And today I want to share with you how Slack has adopted edge-style architecture in order to keep up and get ahead of the growth of our customer base. And at the same time, we also want to continue being agile and moving fast. And more specifically, I'm going to talk about how Flannel, a homegrown, distributed, cache-backed query engine, has been a secret to our scale. How many of you have used Slack before? Raise your hand. Oh, a lot. Well, great. But for those that haven't used Slack before, Slack is a company's hub for collaboration that unlocks not only communication between employees, but also ensures that the right people have the right information at the right time when they need it. Our mission is to make people's working lives simpler, more pleasant, and more productive. So let's take a closer look. So here's a screenshot of the Slack application. As you can see, conversations are organized in channels on the left side, and you can have either public or private or even shared across Teams channels. And besides sending messages, you can upload files, search for messages, search through content, receive notifications, and plug in thousands of apps that you use every day directly into Slack. It really is an ecosystem that enables people to collaborate with each other and get their jobs done. And here you can see all the thousands of apps that have been integrated into Slack, and that was a strategy right from the start. Let's take a closer look at our growth. So when Slack started 4 years ago, the numbers were fairly reasonable for a small startup, but 4 years later, today, we have over 8 million daily active users. So the growth curve has been quite steep in a short amount of time. Let's dive in a little more. So out of those 8 million daily active users, 3 million are paid users, representing 65% of Fortune 100 companies. We are also represented in over 100 companies, and 50% of daily active users are outside of the US. That means our infrastructure needs to support global scale. The other thing that changed over the 4 years is that we went from supporting small teams 3 to 4 years ago to serving today gigantic organizations that have hundreds of thousands of users. And to support such rapid growth of yesterday and today and tomorrow, Slack's infrastructure has to get ahead of that growth. Let's take a look at the progression of the team sizes. So in 2015, the largest team size was 8,000 users. A year later, that grew to 26,000 users. Today, we have customers with over 200,000 users. I think that building should look familiar to some of you. So now let's dive on the infrastructure side. I'm going to walk you through a little Slack's architecture history lesson. So when Slack was first built and the number of users and channels for any given team was fairly small, the laws of physics dominated. So the closer the data was to the end user, the better their experience was going to be. And so we built a fat, greedy client that tried to pull in as much data locally to the client as possible and do it as frequently or as infrequently as possible. Then as our customer base and team size began to grow, that no longer scaled. And so we incrementally made our fat client still fat, but a little more lazy. So we decided what was the right data to load up front and what was the data that we needed to load later. And then around 2017, once our growth chart continued to escalate really rapidly, we had to make some bigger changes. And this is where Flannel came into the picture. Well, I'll dive into the details of Flannel down the line, but with Flannel, we also went through the incremental approach and eventually made it more lazy. And then most recently, we've been focused on resiliency and scaling that out. So let's dive into this fat, greedy client of 2015. What you're seeing here is a really high-level architecture diagram of Slack back in 2015. So on the left side, you see the clients, mobile and desktop, talking to the backend over HTTP. And so this is the initial load where the clients are pulling in all the data they need about the team into the client. And then to keep that data up to date in real time, the clients established a WebSocket connection to the message server, a cluster of messaging servers. And then the backend was also powered by a sharded MySQL data store. So very simple view. To walk through what the connection flow looked like, the client would call an API, rtm.start, and return a HTTP response of a snapshot of the team. And then afterwards establish a WebSocket connection, a long-lived WebSocket connection. So the time to connect for client was a factor of how long it took to get the response back and to establish this long-lived WebSocket connection. So there were some clear advantages at the time of taking this approach. Every Slack object was available locally on the client. User experience was super fast. And it enabled us to move fast as a development team because the backend and the client were decoupled, and all the objects, the client really assumed all the objects were present, so there's not a lot of complexity in terms of logic. But there were limitations as well. The initial connection and reconnection was expensive, in particular as the team size began to grow. The client's memory footprint was also proportional with team size. And this architecture was susceptible to thundering herd. So there was nothing preventing from, all the clients, let's say you're in an office with your employees and they lost internet connectivity. There was nothing preventing all those clients coming back at the same time. So let's take a look at some numbers. So when there were 30 users, the snapshot size that was getting returned to the client was on the order of 200 kbytes. But as it was growing to 3,000, 30,000, it was quite a few megs. And so that was no longer going to scale. And if you recall, in 2015, the largest team size was 8,000 users. So that's already a significant payload size. So what do? We took an incremental approach, and as I mentioned earlier, put our client on a diet and made it a little bit more lazy. So this is, to remind you, this is what the connection flow looked like in 2015. A year later, we made some changes. So instead of returning the entire snapshot of the team, we returned a partial snapshot of the most relevant objects. We still had the WebSocket connection, but then we pruned the real-time events. So it wasn't a complete Firehose feed of all the events, but only the ones that were necessary in order to provide a seamless and real-time experience. For the non-essential objects that we were not loading up front, we asynchronously and in a parallel fashion were fetching subsequently after the initial connect. So this resulted in quite a bit of improvement and reduced the payload size significantly because we were loading less data at client boot time. We parallelized the loading of non-essential objects, and we also simplified the objects as well. But there are still limitations. We were still susceptible to the thundering herd problem if, as I mentioned, example, if there's wireless connectivity issues, or if the clients decided to dump their cache for whatever reason, everybody would come back at the same time. And while we reduced the payload size, there is still a function of team size as it relates to the footprint of the application. So this is when we decided to take more drastic measures. This is how Flannel was born. So Flannel is Slack's edge cache service. It's really a query engine backed by cache and deployed on edge locations. So this is not like Memcache, because it has a more sophisticated query engine, there's more sophisticated filtering. It really is like a simple search engine that is deployed on the edge close to the end users. So let's take a look at how the architecture changed with Flannel in the picture. So we still have the clients on the edges, still mobile, still desktop, but now in the edge regions all over the world, we deployed Flannel. So Flannel had two roles. One was to be the cache for the clients, and two was to populate the cache transparently to the clients. So Flannel would now be the one talking to the backend systems over HTTP to download the snapshot of the team. And then Flannel was the one that would keep the WebSocket connection to get the stream of events to keep the cache updated. In the first iteration, the events were still JSON format, so there was some optimization that we were looking to do there as well. Let's look into how Flannel is deployed. So when a client connection comes in the initial version, we would rely on geographical DNS to figure out which edge region the request should be routed to. And once the request is routed to a particular region, then within that region, we use HA proxy to find the right Flannel instance that has the team model for that particular request and user. If, let's say, you're the very first user from your team to connect to that particular region, then we would load the data at that time for you. But then subsequent users that come... Sure. Do you have should we save questions for the end? Or?
I don't know.
Whatever you
Okay, well, go ahead.
So these Flannel instances are team specific?
Yes.
And you distribute it further depending on the size of the team?
Yeah. So there is affinity, team affinity. So that's kind of how we distributed the deployment and also how the request is routed. Now, as time is going on, where geographical DNS has its limitations, and so we are working on more sophisticated routing mechanisms. That way, when you fail over a region, you can fail it over to a region that actually has capacity or other factors. So what are the general advantages of Flannel-powered Slack? Clients have low latency access to key big objects through the edge pop regions. So if you're located in India, your request is going to get routed to the data center that's closest to you, and the client doesn't have to go back to the main data centers, and also it reduces the load on the data store because the data store is really only accessed by Flannel when the model is loaded. The approach we took, if I were to go back, is Flannel is kind of man in the middle. So we still kept the WebSocket connection, so the clients would connect to the backend through WebSockets. And the reason we did that was to minimize client changes at the time we were deploying this. To make client changes, to make all of this backwards compatible to propagate through Android, iOS, desktop would have been a much larger undertaking. So we optimized for our initial design to minimize client changes. So from a client's perspective, not much had changed in terms of implementation. The other advantages of Flannel, as I mentioned before, there's the query flexibility and filtering. So it's not just a key value lookup. It's not just a key value lookup. It's an actual search engine where we can request top results, sorted, filtered, etc.
So to be clear from the schema, what your write strategy was. So did you write through Flannel as well, or did you write request or request HTTP and go direct with the Java service?
So the write request is a separate flow, which I'm not covering here, but that would go through the Java service, yeah. So the Flannel is more of a cache, a reading cache. So let's take a look at the features. Since a lot of you have used Slack before, let's take a look at the features that have been powered by Slack. Quick Switcher, has anybody used the Quick Switcher? Very few, it's very, very useful. But the Quick Switcher that enables you to find users quickly with a with a quick switch command. Users and channels is powered by Flannel. So these requests don't go back to the server, to the outside of the edge region servers. And this has fuzzy matching and things like that. Mention suggestions and channel membership is also powered by Flannel. So again, this is the performance going to getting these requests from Flannel versus going back to kind of the core data centers. The difference in Flannel, it's 80 milliseconds or less, and so the network latency is quite low there. The channel header up above also is powered by Flannel, as well as a channel sidebar that has information about the users, which users are online right now, what state they're in, etc. So what are the limitations of the initial version of Flannel? Well, keeping the Flannel cache updated is still expensive. It's fire hose of feed events, so we needed to do something about that to make sure it's less expensive. The thundering herd phenomenon is still a possibility. We need to take more proactive action to make sure that the clients can't DDoS our backend systems. And as I mentioned, the cache was on the WebSocket and still in the critical path. So if we were, let's say, updating Flannel model and something disrupted the WebSocket connection, that meant the clients could get disconnected. So what do we do next? Some of the impactful improvements that we did was instead of JSON, we implemented thrift-based PubSub to reduce the number of events processed by 1,000x. So I'll show that right here. So that when the cache kept up to date in real time, we switched the mechanism I was doing it, and instead of getting a fire hose feed, we would subscribe to the teams, the channels that were needed in order for that model to be loaded. You can see on this graph on the left side, on the top graph was the before, and the scale is on the order of 600,000 at the max, and then it went down to about 1,000 at the max. So a big improvement there in terms of the amount of work that Flannel servers had to do and the amount of data they had to crunch. Flannel also was implemented similar to how the original version of the client, to lazily load primary objects. So users, channels, channel memberships. That way, when you're powering up Slack, you don't have to, you may be in 10,000 channels. We do have some people that are like that. And you don't have to load all the channels. We would load just the ones that are in view. And so that reduced the boot time significantly. In particular, this is relevant for those power users that are part of a lot of channels but are not actually actively using a lot of them. And also, this is relevant for really large teams. So the next phase of focus for Flannel was around resiliency. So as many of you know, as scale increases, the likelihood of failures to happen goes up as well. And so our goal was to minimize the blast radius and recovery time of those failure modes. We know it's impossible to eliminate completely and predict everything, and so our goal is to minimize the blast radius and to optimize for quick recovery. But we also noticed that when incidences happened or when failure modes happen, that they happen super quickly at the blink of an eye. And so we knew that the solution couldn't rely just on human intervention or at all on human intervention. So the thing that we focused on was, there was a few different areas, but one of the first ones was automated admission control. So if you have a thundering herd, whether intentional or a DDoS attack, we've implemented an admission control, kind of like a traffic light, that would only allow the amount of traffic that the backend systems can support. That way, we're not boggling down the downstream systems, and the throughput remains steady in what the system can handle. And we implemented this admission control based on various metrics. So for example, whether it's memory pressure on subsystems, whether it's in Flannel or other downstream subsystems, or the number of concurrent requests. And it's effectively kind of a self-regulated system that detects capacity problems and then regulates the traffic allowed. Additionally, we implemented circuit breakers. So circuit breakers were implemented to mitigate cascading failures and to protect our services from each other's potentially bad behaviors. So this is a little different than traffic control, because traffic control is more at the outer edge. Circuit breakers would detect, for example, that the database or our API servers are becoming slow, and so this would back off the number of requests and then retry until the health becomes more stable. Additionally, we've been working on auto-scale and regional failover. So if we have a spike, if a large team decided to post a large announcement in a 100,000 person channel and everybody would receive that announcement, we want to make sure that our systems can auto-scale and doesn't involve human intervention. As well as if there is some network issue in a particular region, which happens from time to time, we want to make sure that we fail over to another region and also fail over to another region that can handle that capacity. Other things that we're working on, so a little sneak peek into the future, is decoupling Flannel from the WebSocket stack. So we know that is, while that worked really well early on and made us move really fast, we want to make sure that we decouple connectivity and being connected to Slack from the cache. And then also we want to move the paradigm of PubSub all the way out to the clients so that the clients know what's in view better than anybody else, what the user is looking at, and so that they would subscribe to only those events that matter to them instead of to all the events. And that's it. Any questions? Sure.
So in the automated mission model, do you have a notion of retries in case there is a genuine number of requests spiking up?
Yes.
Auto retry?
Yes. Yeah. We have retries. We also have the back off, and then it
so it's
will.
On the REST API, that's what you return the retry after this amount of time.
Mm-hmm. Yeah.
Is there something you're persisting these requests on?
The ones that are trying, it depends on the system. So for the message server system does persist like backed up events or requests in memory. So it depends. Yeah, we have it varies from system to system, but yes, we do.
One more question.
Yes.
Great presentation. Second thing is, what about the latency between the messaging server and the cache nodes which are persisted across multiple regions? How are you guys solving?
So the message servers are, which was, I didn't dive into this diagram. So part of them are also on the edge, and then the servers that have the actual message information are in a more centralized locations. And so our latency, so we solve the latency that way. So, yep. Yes.
I was curious with that automated missions scenario.
Mhm.
What is your client experience like in that situation? If they get denied access for that reason, would they know? Or?
Yeah, so ultimately, if our backend systems don't have the capacity to absorb the traffic, then eventually it does propagate to the end user. And so the action here is auto-scaling. But it's, we found that it's better to allow fewer users and the users that are already connected to allow them to continue to operate versus like taking down the entire system by flooding with too much traffic. So
your current client implementation is completely reliant on being connected all the time, right?
with the web, so the client has its own cache as well. So from a connectivity perspective, yes, but you can still just view and load the client. You just can't really interact. I guess the offline mode is not really a feature yet. Thank you. It's homegrown, so we're looking at the various metric depending, like let's say in the case of memory pressure, when we detect that the memory is at a certain threshold that can be configured, then we stop accepting. We basically send a message back to the client that we can. It's like rate limiting message. A rate limiting error code, and then the client starts backing off. It'll try periodically, and once we get over enough of threshold that gets through, then things start flowing automatically again.
Are you trying to identify specific abusive users, or you just order of first come first served?
Can you repeat that again?
When you do this access control, do you identify the abusive users or users who are specifically heavy, or you just try to do per request base?
It's in a general state, it's per request based, but we do have also controls where we can, let's say, take certain team and say, okay, this team we're going to rate limit, but that's more of a manual action. Okay. All right. Thank you. Oh,
right.
sorry. Thank you.